Hey everybody, welcome back to another fun and exciting geometry class. Today we are going to be on page 203 in your books, 203. We're going to be talking about similar polygons. We're actually going to do lesson 4.6 and 4.7 together here. Really, they're connected. The whole thing is about similar polygons, so we'll just join those two together. All right, similar polygons, what are they? Well, it's two polygons whose angles are equal and corresponding sides are proportional. All right, so what does that mean? If I have two polygons and their sides are their, well, let's start with their angles. The angles are equal. So if this angle equals this angle and this angle equals this angle, and, okay, you get the idea. All of the angles have to be equal, okay? The other thing that has to be true is that this side, AB, must be proportional, okay, to this one over here, this A. It's called A prime, B prime. And let me scroll down here and show you why we're using A prime and B prime. It's called prime notation, okay? And this is one of the first times that you've seen it. You've kind of seen it a little bit throughout the book, but this is the first time where really it's important. Prime notation is when an angle or side is transformed. So it's like blown up or it's shrunk down, it's turned or something like that. There's some sort of a transformation that has been applied. In geometry, we use the apostrophe after the letter to show that it has been transformed but remains similar. So, for example, A becomes A prime. This thing right here, the way that we say it in geometry is prime. So A prime. So let's go back up here and look at this. A becomes A prime. B becomes B prime. C, and so on. Why do those become that? Because it's the same angle. It's just we've shrunk down this second shape right here, the second polynomial. So all of these are corresponding. A corresponds with A prime. B corresponds with B prime, and so on. Okay? So if we can prove that AB is proportional to A prime, B prime, then we have proven that they are similar. Okay, right here I wrote the sign for similar is this thing right here, okay? It looks like the little enya thing they put over the N in Spanish, right? Okay, so you put the little enya thing. What's the difference? It kind of looks like one piece of bacon, right? So this is two pieces of bacon, and what does that mean? Okay, that means that it is congruent, or in math we also say that's approximately equal to. But one piece of bacon right there means that it is similar. Okay, so let's go back up here. We could say that A, B, C, D, E, this one right here, is similar. So A, B, C, D, E, okay, so that's polygon. A, B, C, D, E is similar to polygon A prime, B prime, C prime, D prime, E prime. Okay, I can fit that on there barely, but I fit it. Okay, so it's similar. Why is it similar? Because this side is proportional to this side. That's what we wrote right there. And this angle is proportional to this angle, or is equal to, actually. So in other words, everything is proportional or equal. That makes it similar. What if everything is equal? Well, so what if the sides are equal, the angles are equal, everything's equal, okay? Then they're congruent. Congruent means exactly the same. In this case, they're not exactly the same, but they're similar. One is just smaller than the other, but everything is proportional, okay? All the proportions remain the same. All right, to be corresponding, okay, I keep using that word corresponding, angles must be equal and sides must be proportional, okay? So those are corresponding angles. corresponding sides, corresponding angles. In other words, I can't just say that this is corresponding to this. I can't say, okay, let's call this angle A and we'll call this A prime. Well, A and A prime are not equal angles. They're not corresponding. You can't use A prime there. You have to call this something else. We could call this angle D, but we cannot call it angle A prime because it's not A prime. It's not corresponding. It's not, right here, angles must be equal to be corresponding. Or sides must be proportional. So we can't say that the side is prime to the other side if it's not proportional to it. So it has to be equal or proportional in order to be considered corresponding, and that's important to understand. The bottom of the page there, 203, you're going to see this ratio of similitude. What in the world is a ratio of similitude? Well, it's the ratio by which the corresponding sides are proportional. So let's just say that I have a triangle here and a smaller triangle here. Let's say that my sides of this triangle are 3, 3, and 2. Well, if it's in proportion, here's what that means. It means that it's going to be, let's say that I just need 2 of them because we just need 2 of them to be proportional. So if I have 3 over 2, then this one's smaller. So let's say that this side is 2. Okay, so this equals 2. Then what does this side have to be? Okay, well, this is a mean proportional. Okay, so we would get 3x equals 4, divide both sides by 3, and we would get this side must equal 1 1/3. Okay, because it's proportional. It's all proportional. So if we're going to say that this is similar, it has to fit under the ratio of similitude. Now, let me draw a bigger one. Let me go with blue so that it all looks the same. Now, that one's bigger. In order for me to say that that is a similar triangle, it must fit in my ratio of similitude. What's my ratio of similitude? My ratio of similitude was 3 to 2. Okay, so it's got to fit inside of this 3 to 2 ratio because this is a 3 to 2 ratio. So maybe over here, this side is a 5 now. So it has to fit inside of that ratio to be the same. So we need to know what this side needs to be. So we would do the same thing. So now we would say that it's 3x equals 10 divided by 3 divided by 3. X equals 3 1/3. So this one has to be 3 1/3 in order to be a similar triangle. So these are all similar triangles. Okay, so this one has to be 5 and 5 because it's got to match this, because this is another ratio of similitude right here. This one has to be, these ones have to be 3 to 3. So these ones have to be 2 to 2. This one has to be 5 to 5. In other words, they're 1 to 1. These sides are 1 to 1. These sides are 3 to 2 or 2 to 3, whichever way you write that. So these ones have to all match that ratio of similitude. 3 to 2 is our ratio of similitude in this case, in order to be similar. You could have a different triangle. So if we have one more triangle here, but if my sides aren't similar or they're not in proportion, so maybe this one is a 4 and this one is a 3. Well, that doesn't equal. 3 over 2 does not equal. It's not similar to 4 over 3. How do you know that? Well, if you do the math, you get 9 and you get 8. So this one would not be similar. Why? Because it's off. The proportion, the ratio of similitude is off. It's not a 3 to 2. So that one is not similar. Okay? So that's the ratio of similitude. Theorem 57. This is the next lesson. So go to the next lesson. This is on page 204. Page 204. Theorem 57. If two triangles have three corresponding angles equal, then the triangles are similar. So in other words, if we can prove, what's a way to prove similar? Well, if we can prove that this triangle equals this triangle as far as their angles go, let's say that this is 60, 60, 60. In other words, we have an equilateral triangle. Well, if I can prove that this one is also 60, 60, 60, what does that mean? It means that my two triangles are similar. They have to be similar. If all three angles are similar, then it is similar. Use that sign for similar. In Corollary 57.1, this is interesting because hopefully you can make this connection. It says that if only two angles of the triangle are equal respectively, then it is similar. Okay, why would that be? Let's use this corollary 57.1 to prove these are similar. Angle, angle. Well, if you look at this, let's say that one of these angles is 75 degrees. And this angle over here is 30 degrees. If this angle over here on the smaller one is also 75 degrees, and this one is also 30 degrees, you can see how just using angle, angle will actually get us where we want to be. Because we have two angles, we don't need the third angle. You say, well, why not? I thought that the theorem said, if you go back up here to the theorem, it says if two triangles have three corresponding angles equal. Well, hold on a second. If we look at this, how many degrees are there in a triangle? Well, there's 180 degrees total in both of these triangles. And if two of their angles are the same, so minus 75, minus 75, minus 30, minus 30, well, that's going to leave that these are equal. These have to both be 75. In order for it to be a triangle, then the remaining one must also be equal. So you only need to prove two of them. Once you prove two of them, then the resulting angle, the third angle, is going to be equal. It has to be equal. So that's that corollary 57.1. Let's look at corollary 57.2. Two right triangles are similar if one acute angle of the one triangle is equal to an acute angle of the other triangle. This is basically the exact same thing as corollary 57.1. Now we're dealing with right triangles. But notice it says that only one of them. Okay, well, now what's going on? Well, let's say that this one is 50 degrees. And this one is 50 degrees. That's all we need. Okay, we're done. And you say, well, wait a second. How are we done? Because we only have one. No, that's not true. We actually have two. What's our other one? Our 90-degree angle we also have. Why? Because it told us that it was a right triangle. Okay, so we have the 90 and we have the 50. So what's the remaining side? Well, the remaining side has to be 40. It has to be 40. And so that one has to be equal. So then we go back to the corollary 57.1 and then ultimately back to the theorem 57 that all three have to be equal. So it's kind of neat. Corollary 57.2, you only need one if it's a right. Corollary 57.1, you need two if it's just a regular triangle, because you then have the third angle, which then would prove the theorem 57. Okay? All right, theorem 58. If two triangles have two pairs of sides proportional and the included angle is equal, then the two triangles are proportional, and that is called side, angle, side. Okay? Notice here again, these are small letters. It's not side, angle, side, because that's talking about congruency. This is talking about small letter, side, angle, side. And that, when it's small letters, it's talking about similarity. So that's the difference between the capital letters and the small letters. Just keep that in mind as we're going through these. All right. So if I have two triangles and that have two pairs of sides proportional. So let's just do that. So let's put this, I'll make some easy proportions here. We'll call this 4 and we'll call this 2. We'll call this 2 and we'll call this 1. So I'm using these two as the proportional sides. So we could say 4 over 2 equals 2 over 1. What's the key here? We have to make these match. So corresponding with corresponding, and this one is corresponding here. So as long as you keep those the same, and then you can transform it any way that you want. You could put it, well, notice we have a mean proportional right here. So we have 4 equals 4 when we do the means and the extremes, or we verified that this is indeed a proportional triangle. Now, the other thing that we do need in this, we can't just say, oh, it's got two proportional sides, because maybe this other side is different, but it's still 1. Okay, so let's say that it's still 1. Well, if this is the triangle now, it's not proportional. It's not a similar triangle, because we have to have, in order to have this similarity, we have to also have the included angle. It's right there. That's very important that you take the included angle with it. So if this is, let's say this is 80. Okay, so if they're both 80 degrees, okay, now it's proportional. Why? Because we have this is proportional to this is proportional to this, and then we have our angles are also equal up there at the top. So it meets all three. We have a side, the included angle, and a side. And notice that the sides are proportional. They're not equal. If the sides were equal, we'd have congruency, but they're not. They're proportional. Okay, and so we have similarity. Corollary 58.1, if the legs of one right triangle are proportional to the legs of another, then the triangles are similar. All right, this is exactly what we just did here, except for now we're using right triangles. So there's a right triangle and there's a smaller right triangle. But again, these are proportional, so I'll use the same proportion since it's easy to see, 4, 2, 2, 1. If these are proportional, if these legs are proportional, guess what? Now, notice it doesn't say hypotenuse. It says if the legs, okay, why? Because now we have the included angle. The included angle is the 90-degree angle, okay? So there is your leg, angle, leg. But you don't need to write LAL, and that's actually, I should have used small LAL. You don't need to write that. You don't need to write that it has the angle with the right, because it's a given. The right triangle is, the right angles are always the same. So you just need to write LL. Use small letters there again, and that is important that you're not using capital letters. Don't make the mistake I made. All right, Theorem 59. This is the last one, and this is on page 204. Page 204. All right, here, Theorem 59. This is on page 206. Page 206. All right, Theorem 59 says, if two triangles have their corresponding sides proportional, then they are similar triangles. Okay, what does that mean? So if two triangles have their corresponding sides proportional, what does that mean? All three sides. So notice it's side, side, side. So, you can draw your triangle kind of like this, however you want it, and you draw another one kind of the same. And if we say, okay, this side is 4, 2, and 3, okay? So the proportions are going to be off just a little bit in this one, but I'll do 2, 1, and that one comes out to 1.5. So how do you know that? How do you know that that side's 1.5? Well, 1 over 2 is your ratio of similitude. Let me change the color there so it's easier to see. 1 over 2 is our ratio of similitude, and then we have 2 over 4. We could write that equals 2 over 4, and then that equals, and this one was 3, so it's 3, and then this is x if we don't know this one. Okay, so what is that one? Well, the way that you would find it is you would cross that one and cross this one, so you'd get 4x equals 6, divide, divide, and you'd get 4 equals 1.5. So that's how you find that missing side. But let's look at the actual theorem, what it says. If two triangles have their corresponding sides, maybe I should have written all three corresponding sides proportional. So if we can say that they're all three in proportion, then they are similar triangles. There you go. That is similarity in triangles and in polygons. This works in any polygon, not just in triangles. So if you have all of these things the same, if all the angles are the same, all the sides are similar to each other, then you have similar polygons. Some of those corollaries and theorems, they only apply to triangles because they are specific to triangles, like things like right triangles and things like that. But for the most part, the principles that are there apply to all polygons. All right. Well, that's all I got for you. Hope you learned something today. We'll see you later. Bye-bye.